And as people seem to be sitting down, I think without further ado, I'll turn it over to Thibault to tell us about foundations for translational verifiers.
Right. Thank you for the introduction. So let me start by telling you about translational verifiers. The verifiers in general are tools that take as input a program and a specification and try to construct a proof that the program satisfies the specification. And translational verifiers are a popular way to do this, where first, the program and the specification are translated via front-end translation into a program in an intermediate verification language. And then this IVL program is verified by a dedicated backend verifier for this IVL. Example of intermediate verification languages include Boogie, Julian, Viper, or Y3. So specifically in this talk, we are interested in translational verifiers based on separation logic. And so for separation logic, a standard way to verify separation logic is via symbolic execution. And the architecture of translational verifiers has major engineering benefits. So for the same automation, here symbolic execution that can be optimized, this automation can be reused, for example, to build a Go verifier by simply building a front-end translation for Go programs, or a Rust verifier by building a translation for Rust programs or Python programs, and more. And once we have several front ends like this, it is also advantageous because we can build other backend verifiers, such as verification condition generation, which translates the validity of an IVL program into a formula. And all these backends can be reused with different front ends. So translational separation logic verifiers include Julian with front ends for C, JavaScript, and Rust, Verifast with front end for C, Rust, and Java, and Viper with front ends for Rust, Go, Python, and some more. So let me show you more concretely what it means to encode a program and its specification into an intermediate verification language for separation logic. So on the left, we have here a simple parallel program where we first allocate a new point, so a new object with fields x and y. Then in parallel, we will update the fields of q, so q.x and q.y, using another point p. And at the end, we will deallocate p. So here, this is the program we want to verify. And we have a separation logic specification that tells us that we start with ownership of p.x and p.y, where p.x points to 5. And we want to show that at the end, we will have ownership of q.x and q.y, and both will point to 5. So first, we need to encode our precondition into the IVL. And to do that, we can use a statement that we refer to as inhale. So inhale, so the IVL program starts in an empty state, and inhale adds the resources specified by the assertion to the initial states. You can think that it produces the assertion. Then we need to encode this allocation. And this allocation can be encoded using a combination of havoc. So havoc is a non-deterministic assignment. That is, it forgets the value of q. This is because in the front-end program, q will get non-deterministically a new address. And then inhale gives us the ownership to the fields of q. So this corresponds to the postcondition of this separation logic rule. I'll skip for now. I'll show on the next slides how we encode the parallel composition. Then we need to encode the deallocation. And deallocation can be done, so deallocation is the dual of allocation, and it can be done with exhale, which is the dual of inhale. So exhale also takes as a parameter a separation logic assertion. It checks that the resources are in the current state and removes them from the state. And so this similarly corresponds to the following separation logic rule, which says that to deallocate, we need to give away ownership of the location of the object. And finally, we can check the postcondition by using, again, an exhale statement. So now we can look at this parallel composition, and we can use the same strategy because unlike the front-end language that is parallel, intermediate verification language are typically sequential. So here, to encode this parallel composition, we can use the parallel rule from concurrent separation logic, which tells us that we can prove separate triples for C1 and C2, the two threads, and then we can combine their preconditions and postconditions. So first, we need to know what those P1s and P2s, Q1 and Q2 are. So we can ask, that can be part of the specification. We can ask, for example, the user to provide them. We can also infer them. And in this case, we need to check the two premises of the rule. So to check the first primitive, to check the first premise, we can use inhale and exhale as we've seen before, where here we can reuse assignment and field assignment from the IVL. Same thing for the second thread. And finally, we can use the conclusion of the rule with exhale, havoc, and inhale to encode the parallel composition. So you can think about first this exhale here as removing P1 and transferring P1 to the left thread, and removing P2 from the current state and transferring it to the other thread. We have to havoc V here, so to forget the value of V because V is modified in one of the threads. And finally, we get with the inhale, we get back Q1 and Q2, so the two post conditions. So you can think about it as P1 gets transferred to the first thread, and Q1 at the end gets transferred back to the main program. So that is our encoding. And what we would like is that this encoding is sound. That is, if the IVL program is correct, then the front-end program is correct with respect to its specification. And so if we go back to our picture of translational verifiers, what we want is that if the backend verifier reports success, then the front-end program satisfies its specification. And this is the goal of this work. The goal is to develop a general framework for formally establishing this desired soundness property. And because we have an IVL program in the middle, we can actually split this desired soundness property in two. So we can first connect the backend semantics to the IVL semantics that is independent from any backend verifier with this backend soundness step. And in a second time, we can just connect the IVL semantics to the front-end semantics via front-end soundness. And there are several challenges in this approach. The first challenge is how to define the semantics of the intermediate verification language. So as we've seen in the example before, the state of the IVL is a separation logic state. We have statements that manipulate separation logic assertions such as inhale, exhale. And in particular, there is no notion of execution for an intermediate verification language because we don't interpret or execute them. They are simply here to represent verification conditions. Other challenges include the backend soundness and the front-end soundness. So to tackle these challenges, in this work we design, we work on core IVL, a core language that captures IVLs based on separation logic, such as Gillian, Verifast, and Viper. So core IVL contains the following statements. So we've seen inhale, that adds resources, exhale, that removes resources, or havoc, that performs an undeterministic assignment. We also have standard control structures, like conditional, sequential composition. And at the end, we have this custom statement that is used to instantiate core IVL to a concrete IVL. For example, for Viper, we can instantiate it with field assignments. As we've seen in the example, Viper supports field assignments. But there is also another discrepancy that we need to resolve if we want to capture those existing separation logic-based IVL with core IVL. That is, Gillian and Verifast assertions are based on separation logic, whereas Viper assertions are based on implicit dynamic frames, which is a variation on separation logic. And to do so, in this work, we propose a novel generalization of separation algebra that unifies separation logic and implicit dynamic frames. And so now the question boils down to what kind of semantics do we want to give core IVL? So if we go back to our picture, core IVL sits in the middle between some front-end semantics and some back-end semantics. And the back-end verifiers you typically have operational semantics. So why is that? If we look at the two type of back-end verifiers we've discussed, verification condition, there is an existing formalization of the verification condition generation backend for Viper that has an operational semantics because it connects to a Boogie program that also has an operational semantics. And if we think in terms of symbolic execution, there are operations that symbolic execution does. For example, when we go to an if statement, the symbolic execution will split and explore different paths, and this is inherently operational. And on the other hand, we have a front-end semantics that is also operational. We have an operational semantics of our program. So it seems that we want to connect an operational semantics to an operational one. But if you recall the example that we've seen, we actually use the separation logic rules to encode our core IVL program. So we actually want to connect our core IVL semantics to a separation logic or an axiomatic semantics. The axiomatic semantics is connected to the operational one via the usual soundness or adequacy theorem for the logic. And so one key idea of this work is actually to define two semantics for core IVL, one operational and one axiomatic. And we show that the validity of a core IVL program with respect to the operational semantics implies the one with respect to the axiomatic semantics. And here, note that this is actually a surprising direction. The usual direction is really going from the axiomatic to the operational one, the soundness. But here, because of this architecture, we require the other direction. We can then connect the backend semantics to the core IVL operational semantics via some type of refinement proof, which we have to do only one per backend verifier. And we can now prove the encoding that we've shown before sound by connecting the two axiomatic semantics by a technique that we call proof reconstruction, where one gets a derivation in the axiomatic semantics of the core IVL program and can deconstruct it and reconstruct it to obtain the separation logic proof for the front end. So now, in the rest of this talk, I want to talk a bit more about the operational semantics. And here, as I said, we want this operational semantics to be independent of any backend verifier. And for example, we have symbolic execution and verification conditions. Those are very different verification algorithms. So symbolic execution is usually an algorithm that manipulates a list of heap chunks, whereas in verification condition generation, what we do is that we reduce the validity of the IVL program to a logical formula using a total representing heaps as total maps. And moreover, there is no one symbolic execution and one verification condition generator. There are many variations because of many different heuristics, changing variants that might be better for some types of programs, but worse for others. And as I will show you next, this means that there is a choice, that those algorithms have a choice when it comes to existentials, disjunctions, magic wands. So to see why there is a choice, let's look at this simple program. We start in an empty state. We inhale P of A and P of B. So we have both. And then we need to remove P of V for some V. So the question here is, what should we remove? Should we remove P of A from the state? Should we remove P of B, maybe either non-deterministically? And the choice that we make here has a consequence on what programs we consider correct. For example, if we want to exhale P of A afterwards, here we would need to remove P of B. But if we have the exact same program where instead of removing P of A at the end, we want to exhale P of B, then the choice should be P of A. And so to understand why, for example, the first program should be correct, we can look at it from a separation logic perspective, from a proof. So here, we can see this first program as encoding the validity of this triple. So as we've seen, the inhale corresponds to the precondition of the triple, whereas the postcondition is encoded via an exhale. And we can see the exhale in the middle, exhale P of V for some V, as the precondition of, for example, releasing a lock, where that would be a releasing or lock invariant. And this, we can prove the validity of the triple by using the premise, simply by using the consequence rule and the frame rule. So here we can frame P of A. So we remove P of A and we are left with P of B as a precondition, and P of B implies the existence of V, P of V for some V. So this program encodes a valid proof, so it should be considered correct. But similarly, we could have chosen the frame to be P of B, and then the second program should also be correct. And so to capture those different behaviors for different backend verifiers, which are all correct, we use angelic non-determinism in the operational semantics to capture those different behaviors. And here I've shown it with an existential, but this also happens with, as I've said, disjunctions, magic wands, and other constructs, other imprecise assertions. So to wrap up, all the contributions in this work are performed in the Isabelle Proof Assistant. So we present this generic core IVL framework, which is parametric over a generalized separation algebra that captures both separation logic and implicit dynamic frames. For this core IVL, we define a novel axiomatic semantics and a novel operational semantics. And as we've seen before, this operational semantics as both angelic and demonic non-determinism. Angelic non-determinism for exhale, and demonic, for example, for inhale and havoc. And to demonstrate the practical utility of this framework, we have instantiated it for Viper. And we have shown for this instantiation that we can connect it to a novel implementation of symbolic execution in Isabelle and an existing formalization of the verification condition generator for Viper that was formalized and formally validated in last year at PLDI. And on the other side, we build a novel simple front-end verifier for parallel programs. And we show that it is sound. So we show that the whole pipeline is sound. And in particular, the proof that connects the axiomatic semantics of core IVL to here a concurrent separation logic is done via this proof reconstruction, which facilitates the proof. So that's all I wanted to talk about. So this concludes my talk. Thank you for your attention, and I'm happy to take any questions.
Please raise your hand if you'd like to ask a question.
Is this operational semantics a big step? Is the operational semantics that you have there a big step? Is it a small step?
So in a sense, it's a big step semantics because there's both, because there's dual non-determinism. We use this technique where you reduce to a set of states, but you have different reduction. We've explored a bit some time ago also if a small step semantics would make sense. So for example, in Viper, you can prove termination. And for this, to explain what it means to prove termination at the level of the IVL, we might need more of a small step semantics. But it turns out that termination can be seen as, so terminate, we don't have to check termination here, but we can deduce termination at this point, so that wasn't really useful. And there were also some challenges in combining small step semantics with dual non-determinism. So right now, it's big step semantics.
So I was a little surprised that you were using havoc to represent getting a new location for allocation. Do you have any issues with aliasing in the semantics of havoc? Do you make sure it doesn't produce an alias of an existing pointer or something like that?
No, so the way it works, I mean, there are two things. The way it works, havoc doesn't make any assumption, right? It really reduces to everything. But after that, we have an inhale. Yeah, that might be a long way. So after that, we inhale, we add the ownership. OK, I'll have it here. Good. This part here is the one that will make sure. So when you inhale, you basically add resources to your state, but you also prune the possible states. So if you get here, for example, if here Q gets assigned to P, right, you will get non-aliasing from those two, from this. There are other ways, actually, to encode allocation that are more complicated, but that would give you, for example, non-aliasing between Q and P, even if you don't have permissions to P. But here, we choose a simpler encoding.
Hi. Hi. I have a question. Can you go to the syntax of your core IVL?
Sure.
So I noticed here you omitted any kind of looping. Is this because you just inhale and exhale the loop invariant?
Sorry, can you say that again?
I noticed that this syntax here doesn't have any form of looping. Is this because you inhale and exhale the loop invariant?
Yes, so there are, Viper in itself, as for example, or the others have while loops. But ultimately, there are several ways to encode while loops. The easiest one is to you have a loop invariant, you exhale the loop invariant, you havoc the variables that are modified, and then you inhale the loop invariant. So, and in this work, in the front end, the front end for parallel programs, we have a while loop, and we show that this encoding is sound. So this is really sufficient for at least everything that we prove about the front end verifier.
Okay, thank you.
Let me try to ask one more question here. I don't quite understand why you need inhale, exhale, and havoc to be general productions of this grammar instead of basically encoding Hoare triples where you have the other constructs that appear between a precondition and a postcondition. Why would you need to be able to arbitrarily use inhale and exhale and havoc anywhere inside a program?
Oh, you mean as opposed to just calling methods?
Just at the beginning and ends of blocks. where you reduce your original program to a bunch of code blocks, each with a precondition and a postcondition.
I'm not sure if I fully get the alternative. What would be your suggestion? Would you have a different syntax, or would you not even define it, formalize it as a language?
I was thinking a more restrictive syntax, but it sounds like my question is complicated.
So if you're thinking about triples with inhale and exhale, so the encoding of the parallel composition, for example, doesn't really correspond to two method calls, right? So we check them as triples, but then the way, we have a triple P1, C1, Q1, but then we use exhale with P1 star P2.
Okay.
And in general, you can encode other things but maybe that would work too.
Okay. So, okay.